Ooh. So what I'll be doing now is I'll be zipping and sort of packaging the websites that you're supposed to look at in the pre-processing tutorial, and I'll put them on Canvas for you to download for those of you that can't access them from the university website, because IT isn't replying to my questions. I will be doing that in a bit. And then the goal is to just walk through those websites to give you an idea of what's going on there. And as stated per the announcement, you can also find the recording of the GLM notebook in the YouTube playlist for the course. Yeah. And I had to take a phone call somewhere near the end of the recording. So there's actually 2 recordings, but I think you can manage. They're called 1 and 2. So, you know, 1 first, 2 second.
Yeah, because it always connects to the circle. Yeah, but if you want, but at least like what I have. For this one, okay. Because before I get yeah, but now I'm talking.
Recording in progress.
Yeah, sure. So like actually from what we can hire was I don't know if that was the plan, yeah, what I did. Um, what you're looking at, but yeah, no, I was doing this yesterday and I was like, I have no idea what I'm looking at. Yeah, it was. No. It was also not sure about and at the same time.
Wat een leider. Ja, die ben ik nu aan het... Hoe werkt het? Hoe krijgen we die aan? Oh, hier gewoon een USB-C-ding in. Chill. Ja, hè? Maar wat je dan zou willen natuurlijk, is dat je dus ook wel het scherm aan kan zetten. En dat zien we op dit moment nog niet. Oh?
Sorry, ik wil iets aangaan. Nou, zeg bij mij gaat hij niet aan. Je moet een kabel lossen.
Good morning. Yeah, so what I've done is I've uploaded on Canvas the website. So the websites were supposed to be something that you can access through the university IT thing, but it doesn't work. So I've not. Oh, really? Because I just noticed that. That's weird, eh?
Yeah, I don't know. I tried it yesterday. Also now it's working. So for me, it's only.
Oh, I'm sorry. Yeah, no, so I'm going to try to go through that as soon as I get the screen to work. But for those of you that cannot access the website, you can now download it from Canvas. So if you go to the data folder in the files menu, you'll be able to find a reports.tar.gz and prf_lyon.tar.gz, and you can download those to your hard drive and then open those, and you will have the websites there. So you should have access to that. Ja, dus die gast die er net was, die hadden we dus eigenlijk gewoon zijn ding moeten laten doen. En dan was er niet zoveel aan de hand geweest misschien. Was hier toch ergens? Oh ja, hier. Nu is die. Maar de computer is niet aan of zo, hè? Normaal is er gewoon zo'n kastje dat je kunt zeggen van doe mij even die. Yeah, so it's very nice that this room is brand new, but we don't have a screen.
Yeah. Have you tried turning it on?
And off and on again? Yeah.
Perhaps.
Yeah, no, I just fired up a computer here, but I don't know what that's responsible for. So I could have just set off Armageddon. I don't know. Inputs. Let me see. Why not, right? Auto switch. So there's a tip from someone. Sometimes it works if you go to incognito mode, apparently. So I'll try that now. Oh, that doesn't work for me. That's strange. It's my server. I've always been able to access it. But the files are. So let's go to the PRF Lyon one. The other one, the reports.tar.gz, is still uploading. But what I'm going to do is share my screen on the Zoom meeting. So if you log into Zoom, you can follow me going through the website there. Yeah, so you'll not be looking here, but you'll be looking at your own screen. Does that sound like a thing? You can get to the website? Really? Because mine doesn't. That is annoying. Yes, so here we are. Zoom. Here we go. Is everybody seeing this? Right. So I'm starting with the Fmri Prep. So there's two things that we link to. The first is Mri Qc, which is a quality control. The QC stands for quality control. And that allows you to track whether your Fmri went well, right? So that is, are there any obvious problems with the data, and how are they, what problems are those? Yeah. So that's something that everybody tries to run all the time. Like for every time they scan, you run Mri Qc. But first we're going to talk about Fmri Prep. And that is a more general pre-processing thing. So they're both created by the same lab, Mri Qc and Fmri Prep. And they run in a container, so they run from any computer, more or less. And as long as you have a BIDS formatted data set, you can point that software to that BIDS formatted data set, and that will run the entire pre-processing pipeline, right? So the benefit, of course, is that you don't have to write one yourself, and they are actually pretty good, the things that they've implemented. But moreover, we get this added bonus of having a reproducible pipeline, right? So no longer are you sort of stuck with what somebody before you in the lab did with some idiosyncratic pre-processing. No, you're actually running the same as someone else on the other side of the world, right? Everybody is starting to use the same data format, and everybody is starting to use the same pre-processing pipelines. And you can definitely see how that is really powerful, right? If I want to analyze someone else's data, then I can just take their data if they're in BIDS and run Fmri Prep, or in many cases, they've already run Fmri Prep, and I can just take the outputs of Fmri Prep that I'm used to anyway, right? So there's a lot of benefits to using something like this, and this is really where Fmri as a field is going, right? So we used to have all these little islands that were doing their separate things, and now more and more people are doing the same thing. And that also means that there is this sort of critical mass attached to the development of a package like this, and you see that there is a lot of increased investment also in just making it even better and better. Yeah? The fact that it's open source software also means that other labs can contribute, and that also helps a lot. So what we're looking at here on the screen is an output of Fmri Prep, and it has run both an anatomical and a functional processing pipeline. Yeah? So what that means is that in the original BIDS folder, there was an ANAT folder for this subject, for this session. It contained a T1 weighted image, and there were two of them, apparently. And there was a whole set of T2 star weighted functional imaging data in the func folder. Yeah. So that means we had this BIDS data set, and this was used to create this Fmri Prep output. You see that we ran 10 runs for a task called PRF, which stands for this population receptive field mapping type of experiment that I talked about before in the previous lecture. So first, if we go to the menus, you can go to the summary, right? And it just gives you an idea of subject ID and what types of things that we asked it to do. I'll go into that. Then you can go to different sections here for anatomical or for functional, separated by task. You can ask it what it did, right? So how was it run at some point? You can ask it about the methods, and it gives this entire explanation about the different methods that it employed. So people just copy paste this into their paper. That's easy too, right? You don't have to write your own pre-processing method section. That's always a lot of work, and that's been done for you. And then you can check whether there are errors. And in this case, there are no errors to report, but if there were, you would definitely see them there. Yeah. So let's go up, all the way up. Whoop. I'll just click on summary because that's at the top. So let's go through this step by step, right? So you can see the different types of data that were contained in this data set and the different types of processing that happened on these data. So you can already see this sort of brain picture at the bottom. This is the result of the anatomical processing. Right, so here you see guess whose brain, and what you see is these three different directions through the brain, right? The axial, coronal, and sagittal views, and try to remind yourself which is which. Yeah. You see that one of the steps that it's taken apparently is that we used to have 2 MRI images for the anatomy, and now we're looking at just 1. So what apparently Fmri Prep did, or what I know that it did, is that it took these 2 images, it superimposed them on top of one another, and then averaged them. And the effect of that is that you have a better image. Yeah? So every image that you get from the MRI scanner has some amount of speckly noise in it. And by averaging 2 of these together, even if it's just an anatomy, you get a better image. And thereby, any automated processing that you do on it afterwards will also improve in quality. So that's the goal. You also see from the top here that the voxel size was 1 by 1 by 1, which is completely standard. Nowadays, people are moving to 0.8, for example, as a standard resolution for anatomies because of improvements in scanner hardware and things like the IT surrounding it. And that gives you more detail. And I'll go into that later on in the course too. So what you see here is that what they did is they tried to in an automated way, mask out the brain. So what they do is they have this little template of where the brain is in a standard head, more or less. They try to co-register this anatomy with that template, and then they have an idea of where the brain is, and then they can use a bunch of image processing techniques to really find the edge of the brain, right? And there is like many different techniques to be able to perform this operation, and they've chosen one which is reasonably good. And you see that the outline of the brain is, I think, in reddish or something. Yeah. So now that you've found the outline of the brain, of course, then you can use that as a pedestal, as a stepping stone to get to more anatomical detail. Yeah. And so there are yet again, other programs that are used by Fmri Prep to then segment out things like the white matter and the gray matter of, for example, the cerebral cortex, the outside folded parts of the brain, or to separate out the different nuclei of the inner regions of the brain. And I'll be talking about these brain regions, what they do, what their general role is, and so forth in the first lecture of next week. Yeah. So you see that the boundary between the white matter and the gray matter is blue. Yeah. And you see that there is this pinkish outside of the gray matter line also. Yeah. This is great because if we want to have the average signal in the gray matter, we can just take the image parts between the blue and the pinkish line and we have gray matter, right? Or if we want to have the white matter signals, we can just take everything that's inside the blue lines. So that's cool. Now this is still in my brain space. Yeah, so my brain has its own little space. Every brain is unique. And so you have an anatomical space for each brain. But that's not necessarily what you want, right? You want to have everybody's brain in more or less the same space so that you can, for example, average across different individuals or perform some sort of group analysis across different brains. Yeah. Now, just a philosophical remark surrounding that issue is that, you know, everybody is unique, and any sort of method that you try to put people into register, to co-register their brains, if you will, is going to be a kludge, right? Because you're going to make errors, and that means that when you average across different people in whatever space it is, there's errors in there, and that's going to limit your analysis. It's always going to be a problem because everybody is unique. Yeah? But then again, we can't do group analyses in the single subject level, so we need to do something. Again, one of those problems that we know we can try to overcome, but we need to be aware that what we do is never perfect and understand that there are edge cases in which things will break. So here is still that, that single subject anatomy. So all of the wobbly parts of my brain are still here, right? All of the individual parts, my brain might be a bit smaller or bigger or more asymmetric than others, and then you will still see that. So what we can do is take this anatomy and co-register it to a standard template, which is called Mri. That's really the standard volumetric template that we have. So that means volumetric means it's still a volume, right? It's still a set of voxels as opposed to, for example, a surface-based thing. And what you see is that we can take that brain from the initial sort of individual space and then try to co-register it with the template. So what's the nice thing about Fmri Prep is that in many of these images, when you hover over the image, it will go back and forth between the input image and the output image, for example. So what it does here is you see the original image that looks like the sort of darker one, the sharper one, that's the original image. And the other one is then the Mri template, right? So you see how well it has managed to co-register that individual brain to this standard brain. Now this Mri stands for Montreal Neurological Institute. What they did is they averaged together 152 people's brains, and thereby constructed an atlas space, if you will, that other brains can be warped to, right? So this is one example of a nonlinear registration that I'm sure you got from the recorded lecture, right?
So does it kind of give you an idea of how much the brain that you measured is like off from his preset brain? Like to say if you have someone in there that has had a big brain tumor and this is a part of their brain, like would he still be able to do this, or would it like be such a big
That's a very good question. So can you do this, for example, when people have holes in their heads, right? When their brains are even more individual, if you will, right? Yeah, so this problem that I was talking about before, right? It's really strange to warp people's brains in the first place, right? And you can sort of get away with it if people are all similarly shaped in terms of their brains, but especially in these types of clinical situations, you lose that. Now, you have to be aware of this, that this is the case. So you're running into the problem right there. So if people have, for example, had a cerebrovascular attack, which really takes out a part of their brain, you will see this in the warp field. That is to say that the transformation that the computer has come up with to co-register the individual brain to the template, right? So you can inspect that. Yeah? And this back and forth between the two images actually already gives you an idea of how much warping must have taken place, right? So the computer doesn't care, right? It just tries to shoehorn one brain into the shape of another, and it doesn't care, right? How much it hurts. Now, for clinical situations, there are certain solutions to this problem. That is, you can actually give Fmri Prep or other registration methodologies a mask, right? So you can actually draw out where the CVA is in the brain and say, this is the mask for this subject. And then many of the registration methodologies that we use are actually able to, make sure that they don't try to warp that into that standard template. Yeah. You also had a question?
Yeah, the fixed one is that template with the
Yes. So you have, yeah, moving is the individual brain. You see that by the, the fineness of the vein pattern in the middle of the sagittal, for example, right? So that's all unique, right? Whereas the other one is definitely smoother, right? It doesn't have the fine curvings that the individual brain does. But you are looking at the individual brain already warped into that standard space. So probably the shape of this individual brain wouldn't fit in my skull, right? That would give me a headache. I don't want to think about the operation that's needed. So that's one thing, right? So you get to this volumetric space where in principle you can average different subjects together. And I think the general consensus is in the field that you can do this, and it's a necessary or valuable pre-processing step to take, but it is more valuable for everything below the cerebral cortex. So that is the subcortex. And you can think of the brain stem, the basal ganglia, the thalamus, and the cerebellum. And I'll talk about all those different brain regions next week, like I said. So it's more valuable for those lower brain regions because across subjects, they are also more similar to begin with. But this unique folding pattern of the cerebral cortex that rests on top is actually quite problematic. And it's very hard to co-register that in 3D. And for that, we use surface-based alignment. Yeah. Now, the first step to do surface-based alignment is to try to find where the surfaces are. Yeah. And so we use this package called FreeSurfer that tries to find where exactly this sheet of the cerebral cortex is, where it begins from the white matter and where it ends on the peel surface. And as you see, FreeSurfer works reasonably well. If you give it good input images, it will generally be able to trace out the edges of the cortex quite beautifully. So let me try to zoom in a bit. And you see that it really traces the outline of the brain on the outside, which is this peel surface. And you see that it has a pretty good idea of where the white matter goes into gray matter. Right? And of course, once you have this information of where these boundaries are, you have a mesh for the white matter gray matter boundary. You have a mesh of the peel surface, which means that you can do all sorts of computational things with them, like we saw in, you can, for example, inflate these images, and you can project voxels onto these surfaces, like we already also saw in that WebGL viewer that we'll get back to. Whoopsie. So you also see that this is only for the cerebral cortex and not for the cerebellum. That's not actually colored here because we just tend to leave that out for an analysis like this. Yeah. This is also something that's a bit of a shame. Everything in MRI, in fMRI at least, has been focused on the cerebral cortex. And it doesn't, that's not surprising that people have done this because it's, it's just there at the top. And we know that for humans, it has evolved faster, right? So we know that it's important for our human faculties, but it turns out that other brain regions, and specifically the cerebellum that you see at the bottom in the sagittal slices, left bottom, we're starting to realize that region is very, very important for our mental faculties. But when people were scanning, up until a few years ago, they would say, but we can get smaller voxels and we can scan faster if we just take a few slices from the bottom of the brain, right? And then we'll still have the whole cerebral cortex. We'll just not scan the cerebellum. And so if you go in the literature, many people weren't even scanning the cerebellum. So they were really blind to whatever the role of that brain region would be. In any case, you see that we can, for the cerebral cortex at least, get these beautiful surfaces, and they provide us with sort of outline with a sort of common surface space other than a common volumetric space that we can then start to work with. So for example, in the projects that you're going to do that I'll explain on Friday, you will see that all of the data that you'll be working with isn't actually voxel data anymore, it's surface data. Right? And so the visualizations that you will do are also performed in surface space. And the brilliant thing about that is, of course, that if you can plot your data on the surface, you can actually unfold the entire brain and look at it in one go, right? So for visualization purposes, it's actually very efficient to have that surface representation. So that's for the anatomical preprocessing. We'll go into this surface-based processing a bit more when I explain more on the projects, right? But just as a reminder, right, you might think that it's easy for a computer to find these boundaries between tissue types because it's so damn easy for us to do so by eye, right? Oh, I see that, right? But in many cases, scans are pretty inhomogeneous, so a computer gets lost very, very quickly. And so this FreeSurfer program that I'm talking about really is millions of lines of code, and it uses a lot of image processing to get the job done. And if you give it a bad scan, it will fail dramatically. So luckily, there's okay data here. And that's as far as we go for anatomical processing. We could talk much more, but I'm not gonna. We're gonna move to the functional pre-processing, because that's where the types of things that we are interested in show themselves, if you will. So it gives us a summary of all of the different runs that we ran, right? So you get for task PRF in this case, a summary for all of the different runs, and we had 10, so we have a couple of sections here. What you see is that it tells us a bit about what the scans are like, and it tells us a bit about the steps that it's taken to perform this analysis. So what we'll go into in the later MR physics lecture that will be given by Nikos, one of my colleagues at the Spinoza Center. He's an MR physicist. So what we'll explain there is how these images come from the scanner, how they're built up by the scanner, and also what the different artifacts that you can see are like in the images. So one of the things that you get is warpings. So a single subject's functional images, because they have to be acquired very quickly, they're acquired rather sloppily, and that means that they are distorted relative to the anatomical image. So even if you were to place the functional image right on top of the anatomical image, you would see that the functional image bulges out from the brain or pinches into the brain, right? So there isn't really a one-to-one correspondence, and we need to correct for that. So this problem of distortion is caused by something called or related to phase encoding, and you'll learn from Nikos what that is. And so also the correction is based on phase encoding. You just do two different scans. One of them has distortions in one direction, the other has distortions in the other direction, and then you can correct for the distortions because the truth is going to be somewhere in the middle, right? So that's what we do here. So that's called susceptibility distortion correction. So that's phase encoding based, blah, blah. We'll talk about that in a later section. So slice timing correction, we've talked about that, right? In a general functional image, you can perform slice timing correction or you cannot, but it's important to realize that the reason that you would do this is because all of the different slices are acquired at a different time, right? So even if a TAR is 1 second, and you have 10 slices, all of those slices would be 100 milliseconds apart in terms of the time that they were acquired. And the same holds for this. Now then you see that the registration was used, was FreeSurfer's BB register. It's called boundary-based registration. That stands for boundary-based registration. And what that does is it uses these outlines, these meshes that FreeSurfer created for the anatomy. It uses those to find where that functional image fits best with the anatomical image. So really, it's using its anatomical knowledge of that individual's brain to perform a registration between the functional data and the anatomical data that is best. Yeah? So you can also do this without this anatomical knowledge, but discarding the anatomical knowledge, which will only give you a worse result. So this BB register really is the standard. People use it all the time. Now, once you have this co-registration of the functional data and the anatomical data, you know where all of these time courses are in the anatomy of the brain, right? And so what you can then do is say, but I also know that this anatomy of the brain is related to this standard brain in this way. So you actually know also where the functional data live in this standard MNI brain. Right? So what you could do is resample your functional data to that MNI brain. And in this case, that has not been done. But in this line where it says functional series resample to spaces, : it could say MNI. And in that case, we would also have an output of Fmri Prep that gives us the functional data in this volumetric standard space. Yeah. Now this T1 weighted stands for the T1 weighted scan that we acquired for that individual. And that means that we now have functional data resampled to the anatomical space of that individual. So now we have functional data that live in the individualized anatomical space. Now, what we also have is, maybe template was MNI space. So it could be that there is MNI. I'm not really sure about that one right now. But FS average is a surface-based standard brain, right? So that means that the functional data are first sampled onto the surface of that individual. And then that individual's surfaces of the gray-white matter are then co-registered to a standard surface. Like I've shown you in the pre-processing lecture, you do this by blowing everything up to a sphere and then rotating that sphere around. And you can be much more sophisticated about that, but that's the way that you resample from a single individual's surface of a left or right hemisphere to a standard brain. And this FS average stands for free surfer average. And so you have everybody in the same surface space. Yeah. So the data that you'll be working with in the projects are related to this standard surface. Yeah. And the idea is then, of course, that because the folding patterns are so intricate in the cerebral cortex, this is better than doing a volumetric co-registration across subjects. So this error that you get between individuals will be larger if you do so in the volume than if you do so on the surface. And that has been shown to really be the case. So you are much more precise if you sample the fMRI data, the functional time series, to the surface of the cerebral cortex. And then there's a whole bunch of confounds that fMRI Prep also generates. So from this entire pre-processing pipeline, what you get is specific tissue types. And we know that specific sources of noise live in specific tissue types. So you get, for example, you get a CSF time course. So that is how the cerebrospinal fluid moved around, how the signals fluctuated in the cerebrospinal fluid. And so you can use that to clean things up. That is the final practical, or the third practical, I mean to say, that's about nuisances. Yeah, so this I'll outline a bit here, but you will go in far further depth in the third practical. Okay. So we do exactly the same operation on all runs. Yeah. It's very simple. There's no difference between the runs other than that they were required at a slightly different time and that maybe the brain is in a slightly different location, but otherwise they are all exactly the same. So let's go and have a look at a single run and see what's been done to it, because it's quite a lot. These fMRI data, we don't know the units. There are no real units to fMRI data. Right? It turns out that they're also warped. They are also, we need to co-register them to the anatomy because we don't know exactly where they are. There's all sorts of vagueness associated with these types of things. So the first thing is this distortion correction. And what you see here is that I'm resting my mouse pointer on top of that image, and it will show a before after, right? It's like a makeover. In this case, it's a makeover from the warped version to a sort of unwarped version. And then, of course, the intent is that that unwarped version will be able to be overlaid with the anatomy with much higher fidelity than the warped version, right? Because they should be the same brain shape now. They've been unwarped. And so the blue line here gives you that boundary between the white matter and the gray matter. So it gives you a reference that comes from the anatomy. And so the before and after of the image, we can then check whether it follows that anatomical reference more closely after or before, right? Because like all of these other steps, susceptibility distortion correction is an image processing step. And if you let a computer do something and you give it the wrong inputs, for example, it will produce horribly deficient results. Right? So if you do it wrong, if you supply Fmri Prep with the wrong information, for example, you can get really weird things like unicorn-shaped brains or things like that. Right? So that's also why Fmri Prep is so good, is because it gives us this website that allows us to check all of the results. Yeah? Because you don't want to know how many papers are actually the result of someone doing something really funky and wrong with their data and then reporting a magnificent result in Nature or Science, right? That has happened quite a lot. But let's get back to this susceptibility distortion correction. It's actually already a pretty good scan. So depending on how you use the scanner, you will get more or less distortion. And this doesn't have tremendous amounts of distortion. So I just have to find an image where even anything is happening, really. So before, after, before, after, before, after. Here you go. Ah! What happened? Whoopsie. Yeah, so we were here. I'm afraid to zoom in now, but what you see here is that before, the visual cortex was very thin, and then after, it bulged out a bit to conform better to what the anatomy looked like there. So that's what you see right above my mouse pointer. It's worse, it's better, it's worse, it's better. I hope this video is in sync. You see that it bulges out a bit, right? And thereby, the white-gray boundary in the functional data starts to align better with the white-gray boundary that you see in the blue line. Yeah. So this is a definite improvement. And if you were to look at this over the entire brain, this actually improves things in specific locations by enormous amounts, right? Because you're now not looking at a signal in white matter or outside the brain, but you're actually sampling the activity from the gray matter where the activity was generated. Is that clear? So yeah, you're always looking at a mess in fMRI, right? So the things that you are looking at, the raw images, are distorted. You don't know where they are. They have units that you cannot trust. And all of this entire building of software with all these pre-processing steps just shoehorns all of this sort of random shit into something that we can start to try to understand. But it's important that we understand these different steps that we go through. So you see, for example, like here at the brainstem, you see a lot of change happening. That's because the signals there are really, really bad, and therefore also the distortions are worse there. It also means that if you have very little signal and you have a lot of distortion, you have a procedure like this that may pretend that it knows where things originated, but you have to be very cynical of their results, right? So bad signal is also just bad signal because garbage in means garbage out. Now, we of course have 10 runs, so this is a never-ending story. But we also have...
May I ask one question about this?
You can ask multiple questions.
So the reason for changing the brain now is to map it to the average brain, so to say, or do some artifacts or something?
Yeah. So that's a very good question. So this is done in a hierarchical way. So you have now a functional scan and an anatomical scan all in the same subject, right? So then we know that the functional scan is distorted. So our first step is to make sure that our functional data are inside the anatomical space of the subject. Yeah. We already need to do this distortion correction to get there. Yeah. So this is all within the subject. And then after that, we want to see how the subject is different from the average brain. And we need to do another sort of warping step to get to the average brain. But this is a hierarchy. You first have to solve the problems inside the individual, and only then can you go and co-register across the population. Does that answer the question?
Yeah, that's clear. Thank you.
Excellent. Anyone else? Questions? So just to reiterate the point, we are interested in getting the functional data to some standard space. The first step is to make sure that everything aligns within the subject, right? So there's a hierarchy there. First steps are at the lowest level. Now, after we've co-registered the anatomy to this MNI space, and after we have distortion corrected our functional data, it means that you can concatenate these operations in principle, right? And thereby immediately project your functional data into this MNI space, for example. Right? So once you've done both of these steps, both at the lower level and the higher level, it's very easy to combine them and just put your functional data in this standard space. Now, another analysis that we need to do in terms of pre-processing, or, well, this isn't even necessary. Everything that I've talked about up until now is necessary because it's about geometry. It's about putting things in the right place. And you can see how that's important and also necessary. Now, when you do all this, you get a lot of extra information. So for example, we do motion correction of the functional images. You try to align the brain across time, right? Because people move their heads either slowly or fast, and you want to put everything again in the same place. So this is a necessary step. It's a geometrical, correction that we need to perform. But movement also generates all sorts of signals. And if we have a handle on these signals, we know what these movement-related artifacts are, then we can try to correct for them in a later processing step. So in many of these pre-processing steps, what we can generate is sort of what we call nuisances. So that is possible sources of noise that have affected our functional results. And the better we understand the nuisances, the possible sources of artifacts that have noised up our data, the better that we can change them, like sort of what we call this is we can regress them out. Yeah? So it means that we can perform cleanup operations on our data. And like I've explained to you before, when you do a GLM, the battle is with the unexplained variance. Yeah? The more of the variance in the data that you can explain, the better your statistics will be, the better your results will be. Yeah? And so what that means is that if you have handles on noise and you can explain that noise in your functional data, it means that you've now battled your unexplained variance. You've decreased that unexplained variance. Yeah? So that's also what this final notebook will be, or sorry, the third notebook will be about. Now, one source of these noise signals that we might be interested in is, for example, from the white matter, from the CSF, because we're interested in gray matter activations, right? And that means that if we don't expect any signal in the white matter or in the cerebrospinal fluid, then any signal in the cerebrospinal fluid and the white matter you can consider to be noise. And that also gives you a signature of what noise might look like over time, right? If the white matter behaves in a certain erratic way, then maybe there's some portion of the gray matter activation that will behave in a similar way, and that will allow you to correct for it. And so that's what we do. We take from the anatomy knowledge of where the white matter is, knowledge of where the cerebrospinal fluid is. We take those images of white matter and cerebrospinal fluid and we project them into the functional data, and that allows us to trace out time courses of cerebrospinal fluid, white matter, just in general, like noise sources originating from white matter or CSF. And so the first thing that you need to do, of course, is co-register these tissue types from the anatomy to the functional images, and that's what you see here. And just for completeness, what Fmri Prep does is it does so for all of the 10 runs. So this is boring, but just to highlight, right? So blue is CSF because you see that it sort of outlines the ventricles. So that will get like the pulsation artifacts, right? The heartbeat is going to push on the brain, and the brain will move inside the sort of bath of cerebrospinal fluid that it rests in. So you will start seeing pulsation type things there. And here, pinkish is white matter, and you see that it will, that's very specifically white matter. You're looking at the corpus callosum here, for example. And so any movement-related artifacts, for example, are likely to be found in the white matter. So that's all good. Oh, I'm back at the susceptibility distortion correction. These are huge websites. You also see that my battery, I hope you don't see this, but my battery is draining very quickly. And I can even improve the responsiveness of my Mac by closing this website, but I won't. Now, all of these are Roy's regions of interest, that is, right? Like I said, not return on investment. In bold space, in the functional space. Then we need to check, are all of these runs co-registered correctly? So we think that we have been able to place the functional data in the correct space, in the anatomical space, but of course we always need to check this for every file. Now, what you see here is the effect of that boundary-based registration, the result of it, and you see that they are beautifully overlaid. Yeah. This is probably better that you can do it by hand. Right? You can actually you can make like a little video game type thing where you rotate the functional data to align with the anatomical data. You can do that pretty well, but this is doing so in a much more principled way. And so this is better. This does allow you to see that, for example, a functional image is going to be problematic where my mouse is, for example, is where the ear canal is in the brain or near the brain. There is a tissue boundary there between air and the brain, and that will cause signal loss. And so you actually see a hole here in the functional image that's related to this tissue type boundary, the air tissue boundary. This is, you cannot correct for this. There's just no signal there. But the main part here is that you need to see that there's a beautiful overlay. Everything that's black, of course, in the T1 weighted anatomical image is white in the functional image because CSF is colored in opposite directions for the two different scans. But this does give you a very nice way of aligning the two, right? And you can check the alignment also pretty neatly here. Now, this has been done for all of the scans separately, right? Because people can be in different places in different parts of the experiment. They can move between runs, for example. Hopefully, if they even move between runs and not during runs. And so what you see here is that we can go through these and you can flip back and forth in these images. Beautiful way of checking every run. So whenever you do an experiment like this, you check, what is this like? Yeah. Beautiful. I'm now at run whatever, 6 or whatever. You can go over and over. And usually, if you've done your scanning correctly, and if you've done all of the parameters correctly, then this will run flawlessly, apart from this sort of thing that can also happen, right? So here, there was a scanner artifact that caused the brain to rescale to values that became uninterpretable. It also meant that the registration didn't have anything to work with anymore. Right? The functional image didn't have any anatomical detail anymore, and it went completely wrong. Yeah. Now you need to know this sort of thing, right? You need to be able to say, but that means that in run, in this case 7, there was a major problem. And if you didn't have this visualization, you might think, oh, it all went fine, right? You'd be analyzing things that in half of the brain are air. Yeah. And so what you end up doing is making like an Excel sheet that says, okay, this run bad, and so forth and so forth. Yeah. Or if you know that something happened to the parameters in the inputs, you can change that and rerun Fmri Prep. But run 8 was good again, so there wasn't anything really weird happening there. So
is the functional image between runs similar, or is the different image every run?
Yeah, so they are usually placed at the same location. So you'd expect them to be more or less identical across runs. So this happening is weird, but it's a beautiful example of why it's important to visualize these things and why it's important to check them. Yeah, so you expect things to be more or less identical across runs, but subjects do move between runs, right? So people will be in an experiment for 10 minutes in a run. They'll be tired. They'll be, oh, thank God this is over. And then they stretch, right? they can move their brains up to like 2 centimeters in the scanner. And that means that for the next run, your acquisition will be 2 centimeters off. Yeah? That's why you need to do this registration per run to be able to say really for sure, like this voxel was measured at this location inside the anatomy, because that's where you're interested. Yeah, that's where things really need to live. And this also goes, this is separate from what you can also do, which is you can acquire, for example, only part of the brain in half your experiment, and then the whole brain in the other half of the experiment, right? So there is no rule against having to scan exactly the same thing throughout an entire experiment, right? So that's also a reason why you need to do this sort of thing on a per run basis. Is that clear?
Yes, it is. Thanks.
Great. I'm sort of assuming that the speakers will transmit the question also, but. So now that we have the registration results and I've given you the answer to one of the questions in the practical, it's run number 7 that went wrong. So you can put that in the WhatsApp group. We're now going to look at these noise sources that we're going to work with in the third practical also. So they call this a bold summary. And what we're going to look at is these different signal variations that happen in the functional data. Yeah. Now, the first thing that you would want to do is check, is there anything weird happening with the data at all? Sometimes there can be an electrical contact in the scanner that's loose or just jumps loose and then reconnects. There's really weird things that can happen with static electricity and things like that, which means that, for example, the values inside the functional image will just spike all of a sudden, right? So they become 10 times their original value and then go down immediately. So the way of checking for this type of artifact is to just plot the average of the entire brain over time. Did anything happen with the data quality in a really, really fantastically dramatic way? And so that's this GS. It's the global signal. It's the entire, so you saw this brain mask before around the functional data. This is what you get. Yeah. And this is a reasonable subject. It's me. I know how to lie still. I've been lying still in scanners for 20 years. So, you know, nothing weird happened during this run. Now, similarly, you will see physiological artifacts and things like that in the CSF or the white matter if anything is up. Now then, so if anything weird is up. And what you see here is that nothing weird happened in the CSF and the white matter, but you can be far more detailed. So on every time point in the functional data, we actually know how much the brain moved relative to the previous time point. Okay? And when people move, so sometimes people just jerk a bit during a scan, or they swallow, or anything like that. Breathing will also do this. It's really a shame that people breathe in the scanner. And what you will see is the brain just bobbing up and down a bit, right? Now, what happens is, of course, at the edge of the brain, for example, you'll be sampling from air, for example, right? And then the brain moves into that specific voxel. So all of a sudden, the signal there goes from 0 to really high, right? And then you might move back and it goes back to 0. So movement really, really creates a lot of problems in fMRI data, right? Because it just really changes what you are sampling with the voxels that you're recording from anyway. And so what you see is that we, in general, in pre-processing, try to really focus on movement. Movement really fucks you up, excusez le mot, because it is really, really detrimental to the signals. Like in fMRI, we are interested in signals about 2% signal change. Yeah? Movement will immediately give you 40% signal change, right? So artifacts related to motion are going to be orders of magnitude larger than the effects that you are actually interested in. Yeah? And so you can see how important this is. So what we can do is look at different quantifications of how much someone moved. And this will give us in millimeters how much someone moved. So in this case, the voxels in this experiment were 2 millimeters in size. And you see that, for example, the fractional displacement is in millimeters here. The maximal movement was 0.3 millimeters. So that's great. That's fine. You won't have a big problem with movement here. But MRI QC, the quality control thing, gives you similar quantifications from a different experiment with more naive subjects. Well, I will invite you to look at the results for those. There's one paper on Perusol that you're going to read that is about this specific type of visualization that I'm putting right in front of you here, this sort of noisy, blotchy television screen turned off sort of thing. What this is, and you'll read the paper for more detail, but what this is for any specific region of interest in the brain. These are rows, the normalized time course in black and white. Yeah, so if you are interested in a specific region in the cerebral cortex, that's a single line somewhere in the blue. So the cerebral cortex, I think, is blue. Then there's like a brainstem in orange, and there's like subcortex in red, and green is cerebellum or something like that. And what you see here is that even though I was reasonably still, right, and I pride myself on being a good subject because I know how bad movement is, you see, for example, around, let's say 90, so that's here, right, you see that I moved a bit here, and you can actually discern a line right through this graph, meaning that very slight movement of my brain caused signal changes throughout the entire brain. Yeah? Just as a highlight of how bad motion is, you can also see that here at the right top, right, this whole black region here is there because there are these two slight movements that are happening there. Huh? Oh, I'm not seeing the chat. Let me check. Unethical. It depends how you do it. Yeah, so let me talk you through my my torture chamber. In animal research, people actually screw screws into the skull and thereby fixate the animal. Of course, you're not allowed to do that with human subjects unless they are epilepsy patients that are being operated on. I talked about that a bit before, right? So there, they actually implant stereotactic screws in the skull to be able to target things very specifically. Right? Also for deep brain stimulation operations, this happens. But unethical definitely for, you know, just healthy subjects, participants in an experiment. When I do an experiment, I have a custom-made head cast where it's like a helmet. The outside of the helmet fits exactly into the scanner receive coil, the helmet that you place yourself in. And the inside is a 3D scan of my own head. So it's like millimeter precision. I put myself in it, I go in the scanner, and the only thing I can do is a bit of this, but otherwise I'm totally stuck, right? So that's why that helps, right? And it's been shown that it helps. I used to have to, and this was like earlier, like in the 2000s, we used to use bite bars. So we have this entire very stiff apparatus, like an arc that goes over the head of the subject, and it has this very stiff sort of appendage to it. And there's like a little dental impression thing attached to that. So you put someone in the scanner, you place that dental impression that's unique to the subject's teeth, you place that inside their mouth, and you screw everything tight so they cannot move. Of course, they can still move if they really want to, but it's the idea is that to give people like an impression of whether they have moved or not, because you know your upper teeth are connected to your skull in most people, and that gives you a very good way of remaining still. So you really need the subject to help you in their remaining still, but yeah. So there's also ethical problems with that. A naive subject will not tolerate this because having something in your mouth like this will cause you to salivate, and people get panic attacks, and it's just not so very friendly. So this is also being phased out. Normally, unethical. You can just use tape. We use tape. You just place tape over someone's forehead, not such that they will be fixated really, but that they will feel whenever they move. Because in general, you move so slowly, you don't really notice that you're moving. And so that really helps to give people a reference of where their heads are, and diminishes movement quite a lot. It's quite strange that this is not really something that everybody does. People really don't realize how bad the subject's movement is. Rick, I hope that answers your question regarding ethics. Yeah, there's it's a whole there's a world of different techniques to immobilize people. Yeah, I think we're up for a break, right? I am. Yeah, let's have a slight break. Then I will stop the recording and tell you a story about how I was a subject on Friday. Resume the recording, because briefly I think I want to go through Mri Qc Outputs that you can download from the files data folder on Canvas. It's a huge tar.gz file at 2.4 gigabytes, but it also contains a lot of information. So what I want to do is quickly go through Mri Qc. It's a bit briefer than Fmri Prep, but it will give you outputs that partly you've already seen, and partly are really geared towards quality control, so they're slightly different. So the file that you want to focus on is this bold_group.html, which gives you an aggregate of all of the information that Mri Qc has amassed, running through an entire experiment of 40 subjects, each with 7 or 8 different functional runs. So what you end up seeing is these quality control measures that are derived from each run separately, but there are something like 300 runs in total, so you end up seeing 300 dots. Now, each of these quality measures gives you this scatter plot, in which in many cases what you want is for these measures to be low, because they get higher when people, for example, move more. So what we're going to focus on is TSNR. Let me check, because there's a few that I'm pointing out here. We'll look at some SNR, TSNR, some movement, DVARs, and fractional displacement. So yeah, let's do that. So we'll always return to this, which is the summary over the entire group, right? This gives us a nice dashboard to look at the entire data set. So if you end up doing an internship at a lab that does fMRI, just dazzle your supervisors by running this, and you'll be able to point out all these intricacies in the data set, like this subject moved a little bit more and this and that, and you have it like that, right? So yeah, pro tip. So SNR, I think that was the first one. So let's just pick one at the, pick one at the top, SNR here, right? And pick one at the bottom. So if you want to know exactly what these numbers mean, there's a link to the Mri Qc website that tells you where they came from, right? I'm not going to go through each and every one of them. This is the story of my life, of course. We still have 10 minutes or so? No, we're already done? Yeah, who knows, right? We'll see. Yeah, so we still have some time, right? And we don't have to shut down the screen, so yeah. So I'll go through SNR quickly. So I'll just click one of these points. That's a nice thing about this Mri Qc thing. You can click these points, right? The hover tells you what this is. And you can click, and then you get, it will bring you. Hopefully, yeah. Ah, here we are. I just clicked another one, but you can click one and then you get to the, and you see that the MR images are not so good. Or wait, these are reasonable. So what are the things that we are looking at here? So we have the mean image over time, right? So that is a single anatomical image. And you see this is a T2 star weighted image with the white matter being dark, right? Now, what you can also do is look at the standard deviation over time. That's how variable was the data in every voxel during the run. And this is after motion correction, right? So you correct for motion so that you know that every voxel is a voxel, is in the same location, then you can check. And what you see is that you see a lot of variability on the outsides of the brain. Important that that's where a movement brings something that was 0 before into something with a high value and vice versa. So movement is a great contributor to this. What you also see is this sort of X shape near the brainstem. That is where the arteries enter the brain, enter the skull. And what this means is that anything near the brainstem will be pulsating like a word that I can't say, right? So it will be on every heartbeat going like boom, 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 right? And you can imagine that that happens during the TR. And so this causes a lot of signal to be generated, and it's really a shit show, right? This is not a region of the brain you want to be scanning. And if you do want to scan this, you need to take all sorts of mitigating precautions. Yeah. So that's the standard deviation image. In a bad subject, you will be able to pick out, of course, because this standard deviation is going to be higher. Okay. Now here you have exactly that same plot that we had before. Same voxel size as we also saw in the Fmri Prep example, but you see that there's much more movement, and this is a reasonably good subject, right? Here, for example, the run ended. So this experiment was running for some minutes. The duration of the experiment depended on what the subject did, and if they were fast in the experiment, the run would end, but we couldn't stop the scanner. So the scanner had to keep scanning for a while. And this, so you, as a subject, you're doing really your best, and the experiment ends, and then you're like, okay, what do I do now, right? So I'm seeing the computer screen, and we're just waiting. So people start moving. Now, what do you see? People start moving. And so this is a very clear example of what happens when people move. You see this enormous spike of signal being generated throughout the brain, right? And if you were to look at a movie for this, you would actually see this movement also very, very clearly. Yeah, then they zoom in and they really focus on where the brain is. This is reasonably homogeneous. You see a hole here in the frontal cortex. That's normal, yeah?
Like in your, with your head, you said like with the black white dots, it was less fine grained than what you showed here, right?
You mean the this one, the carpet plot?
Yeah, that one.
Ah ja. Ja, jullie, oh, jij geeft hier om 11 uur college? Oké, ja, dan gaan we er vandoor. Ja. So what you have here is this is a much noisier brain. So it's going to go up and down very, very quickly. And that also means that the black and white will be, you know, following each other very, very quickly. And that makes it look more fine-grained, but it isn't necessarily, yeah? So the voxel size is exactly the same. It doesn't have anything to do with the resolution. I'm going to stop the share and continue this afternoon, I think. Maybe supplement this a bit, yeah?